it's Ben with Team Royell again, here today to talk about RF. Before we get started though, make sure that you like, share, and subscribe right down there, and help us out by spreading the word about our new Team Royell YouTube channel. We look forward to bringing you many more videos like this one. But today we're going to be talking about RF and understanding RF basics. Now I'll be the first to tell you, I am no RF engineer and I definitely don't claim to know it all. However, these are a few slides that I've put together for training my guys on what RF is and how it works. The reason we do this is because a lot of people think RF is just magic, it just works. You turn the radio on, they connect, great. But there's physics involved, and so we need to kind of understand that whenever we're going out to do installs and put up equipment, so we don't necessarily rely too much on the fact that this stuff just works, but we understand that we have to make it work great. And so we're going to dive right in and talk about what is RF. Here's a brief overview of what we're going to cover today. I'll try to take my time as I go through these as best I can, but there's a lot to cover, so bear with me. So first we're going to talk about what is RF. So radio waves are created by inducing electricity into a component. And when we do that, it emits an electromagnetic wave. And therefore you get a radio wave. So RF simply stands for radio frequency, which we'll get into the second component of that word. Typically what we deal in is microwave and millimeter wave. So microwave is 3 to 30 gigahertz roughly. Millimeter wave is 30 to 300 gigahertz. So we'll be talking a little bit about some of the words that are associated with wireless technology. First couple are frequency and wavelength. So frequency is the number of electromagnetic wave cycles that pass a given point per unit time. Wavelength is the distance which the fields of this wave repeat themselves. So as you can see in our diagram here, you can see that the wave is a constant wave, just like you would think out in the ocean. Same thing applies here. As you can see, the wave cycles per seconds, those are measured in hertz, are different depending on the frequency, right? So kilohertz, for example, 1,000 waves per second. Megahertz is 1,000,000 waves per second, and gigahertz is 1,000,000,000 waves per second. You can tell that based on the frequencies, it changes the wave structure, the amplitude of the wave. Another thing that I point out here too, and it seems a little off pace, but I also make note that we can change the way that these waves exist in the world. So we can do this by, a lot of folks understand that there's dual polarity now in almost all new technology. So what we're doing is we're using two different radios, and we're emitting these waves on different vertical planes or horizontal planes. This gives us all kinds of new possibilities. We can do MIMO, dual TX, dual RX, and things like that. So just a little point, when we talk about MIMO, we talk about dual polarity. We're basically doing the same thing that all these single polarity radios used to do on a single plane, but we're doing it on dual planes at the same time. Bandwidth. All right, so this is kind of an interesting one. It's a key concept. The amount of information that's transmitted by an RF signal scales with the bandwidth of that RF signal. So typically bandwidth is used to measure electronic communication. Okay, it's the width of the range of the frequencies that an electronic signal uses. I'm going to get into a little bit more of the details of this. This is the dictionary.com definition. But you can see here it's the range between your lowest frequency and your highest frequency based off your sender channel in a specific spectrum. So what does that mean to us? Well, number one, when we're doing channel planning, obviously we want to know what kind of bandwidth we have. How big is the band? Like in 2.4, for example. Not very much channel space to go around here, so the bandwidth is obviously limited. But we need to know that if, say I'm on channel 1 and it's 20 megahertz bandwidth, then we know that we have to space a certain amount of frequency off of that to get another clean channel, to get another open area of bandwidth. So it's just something to keep in mind, and we'll come back to it once we start talking about how we put data on on the RF side. All right, so data to RF. Let's take a look at how we do that. So some of you may be familiar with very old concept binary. So binary data, it's been around since the beginning of time, and basically it's a numeral system that basically is just ones and zeros. That's the layman's explanation of it. You know, 0 is off, 1 is on, and so we can use binary to basically transmit anything we want to communicate. It's just a series of you know, algebraic, basically pieces put together. Let's call it that. So knowing that we use binary in computing every day, how do we transfer this knowledge, this binary communication into RF? So pretty straightforward. We do it by modulating the signals, right? So there's frequency division multiplexing, or orthogonal frequency division multiplexing. Typically, like for example, FSK radios. A lot of people remember the Canopy days, FSK, frequency modulation. So basically what we're doing is we're just modifying the frequency just enough, just a little tiny bit, or the amplitude or the phase. We're basically modifying it just enough so to determine whether or not it's a 0 or a 1. Okay, so we're modifying the radio wave to understand which binary piece of data we're wanting to send it. And this is all happening very, very quickly. So duplexing is used, either frequency division or time division. Time division is very much a Cambium thing. You know, ever since GPS sync came out, and we allow for time slots for the downlink and the uplink, and each frame gets a certain amount of time dedicated to the downlink and the uplink. And so, as you can see in this diagram here, it's pretty straightforward. The difference of, you know, the uplink downlink switching that happens, and so we allocate different chunks of each frame in the channel to flip between the TX and RX of this modification of the frequency that we just talked about. So as I just stated, you know, each packet is given a different slot depending on the different variables that we talked about. So you can see there that there's a little bit of guard time, but then you have station 1 might TX while station 2 RXs, or station 1 RXs while station 2 TXs, so on and so forth. Cambium has been very good about this with their access points. They're all talking at the same time. They're all receiving it at the same time. That's where your GPS sync comes into play. So you don't have noise. You don't have stations trying to talk over top of each other. So spectrum. Here's a fun chart that I threw in here, just kind of keep it lively for my guys. So spectrum is kind of interesting to look at. Again, we go back to this concept of the radio waves are physical. They're a physical being. They're not just magic floating throughout the air. It's not like I can just pop a image into the air, carry it with me, float it down the hall like a bubble. It's a radio wave. It has to travel. It has to be sent and received. So one chart that I threw in here is to keep in mind that radio waves have physical size to them. So you can actually compare, as you can see there, that, you know, microwave ovens, I point this out to my guys all the time. Microwaves are on the same frequency, same spectrum as wireless routers. Some people know that, some people don't. What's the difference, right? People say, well, doesn't that mean that my wireless router will cook me like it does my chicken nuggets? No. If you look at your wireless router, and we'll get into this a little bit later, the power levels are significantly different. You might have a very, very tiny little half of a milliwatt in your wireless router, whereas you have 1,000 watts of power energized inside your microwave oven. So there's a huge difference there. We'll talk about that here in another few slides. But you'll also notice that, you know, as that, you know, wavelength, as you see it to go down, is why we get things like X-rays. The reason we can see through the skin, and the reason we can get down through the body layers is because it's such a small radio wave. It's capable of penetrating more than what, for example, the size of a TV broadcast or mobile phone radio wave would be. Another fun slide I like to share with everybody is the United States frequency allocations. This slide, you can't even see it. Best thing to do would be go look it up on the internet. But it's very interesting. Look up 2, 4, 3 gigahertz, 5 gigahertz, some of the 900 megahertz, the unlicensed stuff that we get to use, some of the licensed stuff we get to use, and compare it on this chart to the chart as a whole. And you'll start to realize why frequency is such a valuable asset in our industry. But most of this is United States government allocation, but it's worth a look. So go look up the United States frequency allocation chart and have fun with that one. So power. So power is kind of a big one. It's related to the energy of the wave. It gives us a feel of distances that we can communicate over, how pure the communication can be over that fixed distance, and helps us understand how much energy can be delivered to a target. So TX power is the total net output power of the transmitter. It's typically measured in dBm or milliwatts. Basically 1,000 milliwatts equals 1 watt. So dB, a decibel, I'm going to read this per the line, because see, a decibel is a unit for expressing the ratio of two amounts of signal power equal to 10 times the common logarithm of this ratio. So it has to be relative to something. And that's the point of reading this out loud. In other words, for example, dBi is isotropic. It's forward gain of an antenna compared to the hypothetical isotropic antenna, which uniformly distributes energy in all directions, whereas dBd or dipole is the forward gain of an antenna compared to half-wave dipole antenna. So, and I think I talk about it in the next slide. Well, we talk about power levels. But anyway, point being is, just like you have a dB of sound that you might measure, that's different than what we might measure a dB of radio wave, because it's in comparison to something different. So just keep that in mind when we're talking about dBs. They don't equate to the same thing all the time. I do talk a little bit about power in watts to dBm. One thing that I point out to my guys is the kind of age-old, for every 3 dB, you double your power, right? So this chart shows you that. If I'm at 8 milliwatts at 9 dB, and I go up 3 dB, which would take me to 12, I doubled my power to 16 milliwatts, right? So age-old adage, every 3 dB you double your power. So when you're out there thinking, well, does 3 dB make that big a difference when it comes to my access point? Absolutely, you're doubling your power every 3 dB you go up. So this is where we talk about the typical RF deployment. Okay, so in our industry, it's an access point, it's a subscriber module, usually antennas on both sides. How do they communicate? How does that work? So we have a transmitter, that's our access point, antenna 1, the environment, antenna 2, and our receiver, which is the subscriber module. So a couple different things. If we're wanting to have the best possible connection between these devices, here are some of the tasks that we have to go through. First of all, we increase our TX or transmit power, right? So we want to maximize the range that our access point will allow. You can see the little mouth there yelling. So there's a couple things. Obviously, every country is going to be have their own government regulations on that, how loud you can talk. And you might have some more low-powered applications in the sense of like Wi-Fi deployments and things like that. So we have to be mindful of how much power we can put into our radio legally. So the next thing we can do is we can improve the RX, or the receive sensitivity. So this is specified in dBn. Every 6 dB doubles the RF link's range line of sight. So in other words, my point there is, again, 3 dB each side. 6 dB, it's going to double your RF link's range, in theory, line of sight. But I talk a little bit about what is RX sensitivity, right? So it's a measure of how well the receiver performs, and is defined as the power of the weakest signal the receiver can detect. So in other words, to layman's terms, basically, how much noise can I hear before it starts to affect me? right? I can have a conversation in a loud room with someone, but at some point in time, this noise around me is eventually going to interrupt my conversation. Okay, so our RX sensitivity is that level. What is that level that's actually going to start to affect how I communicate with the access point from the subscriber module? So we can, do things like obviously increase the sensitivity, make it to where the radio is capable of, having more noise and still operating properly. Or we can try to eliminate some of that noise, put a directional hearing aid on or whatever, for example, as a figurative example, not literal. But we can also increase antenna gain. So more gain means more directional. That can be good and bad. It depends on what you're working with. Sometimes you want a broad antenna so you can, makes it easier for the technician to aim. It receives a little bit better. It's a little bit, more, what's the word? Accepting of flaw. Whereas more precise, more directional antenna is going to be capable of doing better for you performance-wise, but it's going to be affected by more weather and trees and so on and so forth. You always want your antenna cables to be as short as possible. Obviously, you have loss in an antenna cable. And then we talk a little bit about government-regulated EIRP. It's the TX power plus the antenna gain. So we have to explain that. What is EIRP? Everybody's probably heard it. Do you know what it means? Effective isotropically radiated power. Sounds fancy. Basically, all it is it's the amount of power that the antenna will eventually emit. It's going to produce during the peak power density observed in the direction of the maximum antenna gain. So in other words, it's taking how much will it focus that energy from your radio transmitting, how much will it focus, what's that combined EIRP, and then that's typically what the government goes off of when they talk about what kind of power is legally allowed. So we've maximized our range, we've improved our sensitivity, increased the gain on both antennas. The only other variable is your environment. So clear environment of any obstructions. So whether it's visual, line of sight, or RF, radio line of sight. And so we'll talk a little bit about that here in the next slide. So the Fresnel zone. You can read that definition if you want. Think football. Football, Fresnel, football. So this is what I tell my guys all the time. Fresnel zone is the key to deploying a happy wireless connection. So when radio waves are emitted, they don't just emit in a laser beam. And this is probably the most important out of all these slides. If you fast forward and show the rest of your team at your company, fast forward to this slide and move on from here. All the other stuff was basically just RF jargon. This is one of the most important things. There's a Fresnel zone, and the radio waves emit into a radio wave inside this Fresnel zone. Different technologies are going to be different size Fresnel zones. I think I put that in the slide coming up. But it's a football-shaped path, and you want to make sure that when you're deploying antennas, you take into account what the Fresnel zone is between the two antennas. You can see here in the diagram that obviously if we had trees in the way, you have zone 1, zone 2, and zone 3. We want to make sure that this path is going to clear as many obstacles as possible in that Fresnel zone. So you can see there that we raised the antenna and we got above those trees. There is a way to calculate it. Different technologies are going to have different Fresnel zones. So you can see here like a 900 megahertz versus a 2.4. At 1,000 feet, the 900 is 16 foot, 2.4 is 11. 1 mile, it's 32 foot versus 21. And so each technology is obviously going to be a little bit different. But nonetheless, there is a physical structure there. Again, I'm going to jump backwards here. This structure, so the distance between these two antennas and the size of that structure has to be accounted for. So when your technicians are out there and they're doing an install, and they say, I have line of sight because I can see through a hole this big through the trees, the tower. That's not line of sight. That's line of sight if you were installing a laser, which you're not. You're installing a radio that emits a radio wave. That radio wave has to build. So, probably the most important slides in the entire presentation our Fresnel zone. So, quick summary. Understanding what frequency is obviously is going to help you identify the capacity, the penetration through noise that you'll be able to achieve. So understanding what bandwidth is will help with channel planning and setting up in-home wireless networks and better understanding of how your network works. But most importantly, in my opinion, for your guys that are going out there and doing this every day, is what is a Fresnel zone, how it affects your installations. Be mindful of that. I threw a few extra links down here of some of the material that I got for this presentation. I know I kind of rushed through it, but I'm trying to keep my YouTube videos as short as possible. So if you have questions, feel free to add a comment or email me directly. But again, like, share, subscribe to our YouTube channel. I hope this helps you guys out there. And as always, look forward to your feedback. Anyway, that's all for today, guys. Thanks for stopping in. As always, like, share, and subscribe. Hopefully, I know I kind of crash course, but hopefully this is helpful to all of you out there. Again, I usually evolve on it a little bit more whenever I'm in my training sessions with my guys and there's time for Q&A. So feel free to hit me up in the comments or email me directly and ask your questions that you might have. I appreciate you stopping by and taking a look at Team Royell's RF basics, and hope to see you next time. Thanks.